Okay, let's look at number 24. What do we got here? So there is no snow on Janet's driveway when snow begins to fall at midnight. So that's important to notice. So we have basically a point. I think you'd agree. I'm just going to kind of make a note of that. We have the point 00, right? So at time 0, which is midnight, there's no snow. Okay. From midnight to 9 a.m., snow accumulates on the driveway at a rate, right? At a rate. So this right here is a derivative at this rate, okay? Which is measured in cubic feet per hour, where T is measured, yeah. Janet starts removing snow at 6 a.m. So T equals 6. The rate G of T in cubic feet per hour at which Janet removes snow from the driveway is given by this piecewise function. So again, another rate. So I want to kind of just take a second here so we kind of understand what we have. So the first thing we have is we have snow falling down on the driveway. So in other words, and we have this rate of change, right? This rate of change represents the rate at which snow is falling on the driveway. So I'm going to just to kind of summarize what I have here. This function right here represents snow falling down, right? So it's building up on the driveway. Then this other function, this G of T function, right, represents her taking snow off the driveway. So this represents snow leaving. And that's kind of important, right? That we know the direction for both of these. One is where the snow accumulates, one is where it gets removed. Okay. How many cubic feet of snow have accumulated on the driveway by 6 a.m.? So all we want to know is how many cubic feet have fallen on the driveway. This does not involve anything being removed, right? In fact, she doesn't even start removing till after 6. So what we can do for A is I can take the initial amount of snow that fell on the driveway. I think you'd agree that's just 0. And I'm going to add to it the amount that has fallen from time 0 to time 6. And I'm going to use my rate of change function for snow accumulating. So I'm going to be using the f of t function to figure out that value. So in this case, right, it's all just a calculator question at this point. So I get, when I plug it into my calculator, I get either 142.274 cubic feet or 142.275 cubic feet. Don't forget, please go out to 3 decimals at the least. Okay, truncate around, but go out to 3. Do not go out to 2 or 3, or less than 3. Okay, let's move on. Letter B. Find the rate of change of the volume of the snow on the driveway at 8 a.m. So we're looking for the rate of change of the volume of, so now this is a little different. And this is kind of why I emphasized this piece right here. Okay, this line that I wrote. The reason is, I think you'd agree, so now we're looking at the rate of change of the volume of the snow. Well, we have to look at two things. We have to look at the rate of change at which the snow is building on the ground, right? But also she's removing snow. So there's snow going in, there's snow going out. So what I have to do is I have to take those two together and I have to combine them. So what I'm going to do is I'm just going to create a brand new function just for kind of ease of use. So I'm going to let S of t, and this is going to represent the volume. So we'll say equals volume of snow on driveway. Okay, so and this function, right? This is represents it equals if that's what that's what it equals. What is so in terms of our formula, right? Well, what does S of t equal? Well, it equals since we're talking about rate of changes here, it's going to represent it's going to equal the amount of snow falling on, the rate of change of the amount of snow falling on the driveway. So the rate of change of snow building up on the driveway, which was given by F of t. But then we're going to be subtracting the snow she's removing. So G of t. Okay? And then from there, let's see. We have to figure out what it is at time 8. So I'm going to evaluate my function at time 8. And that's going to give me either, and again, you can use this, there's two different numbers here. You're going to get either approximately negative 59.582 feet cubed per hour, or negative 59.583 feet cubed per hour. So before I leave that one, I just really want to emphasize here, what did we have to do? They gave us two rates of changes. F of t represented the rate of change of snow falling on the ground. G of t represented the rate of change of snow leaving, right? Of her removing the snow. If I want to find the rate of change for snow on the driveway at any time, I have to take the first function and subtract the second one, right? Because at like time 7, not only is snow falling on, but snow is being removed, right? So I have to subtract those two. Okay, let's continue. Let's grab, I'm going to do a little grabbing here. So I'm going to grab, actually, I'm going to grab my I'm going to grab my, let's see, well, let's read the question first. Let H of t represent the total amount of snow in cubic feet that Janet has removed from the driveway at time t hours after midnight. Express H as a piecewise function. So let H of t represent the total amount of snow in cubic that she's removing, right? So this function right here was the rate of change in her removing. But now we have to kind of find a function that gives us the volume being removed. Okay, so we know we're going to be kind of integrating that function, but we don't have to worry about the F of t function at all right now because this is just for snow being removed. So let's grab a couple things here. First off, I am going to grab this, because obviously this is pretty important. And then I'm going to grab the question just so I don't miss anything. Perfect. Okay, so what do we have here? Whoops, that's a little tiny. Okay, so we are supposed to create something that represents the volume. So I think you would agree. Let's just kind of go through the given times here. So first off, we know that since we always want to kind of start from where, we always want to start these functions from where we begin, we know that at time 0, there's 0 amount of snow being removed, right? Then what can we do? So let's continue. Now what I'm going to do is I'm going to look from, let's go from time, what is it? 0 to 6. So let's look from time 0 to 6. So from 0 to 6, let's think about what she's doing. She's doing nothing, right? According to this, she's probably still asleep. So what are we going to do? Well, I'm going to take my initial amount, h of 0, and I'm going to add it to the displacement of g. Well, actually, hold on one second. So from 0 to some time, right? This is just, remember, so I'm not using a number here. Well, let me just write down what I got, and then I will kind of explain it in just a second. Okay, so let's talk about this function. This is going to give me the amount of volume of snow within the first 6 hours, right? So we start with the initial amount, which is 0, and then we add to it whatever the displacement that we're looking at. So I put a variable here and not the number 6, because this function right here is going to give us, we can evaluate this function from any time from 0 to 6, right? Well, not really including 6, just under 6. So for example, if I wanted to find out how much snow had fallen at time 4, I'd replace t with 4. So that's why I'm using a variable and not a number, because they're not asking for this specifically at 6. They're asking for any time through 6. Okay. Quick reminder: these can't match, and that's why they're different variables. That's all. Okay. So s was just a kind of random variable that I used. I just wanted to make sure it was different from t, which we've been using for time. Okay. Let's continue here. Let's continue here. So for that one, I think you'd agree, this is going to be equal to, let's keep it up, 0. So it's going to be equal to, h of 0 is 0 plus the integral from 0 to t, and our rate of change in this case specifically for g of t is 0 ds. So this whole thing is going to be equal to 0. Let's continue. So now we're going to look at what happens from time 6 to, I think it was 7. Yes, from time 6 to time 7. So from 6 to 7, let's think of what we got here now. We have in this case, I'll come back to it in a minute. I want to look at the less than or equal to, the greater than, and less than symbols. I'm going to come back to it in just a minute. I'm going to kind of deal with it after I've kind of finished setting everything up. I just want to make sure I'm using the symbols correctly, which for the first one, I am not. Okay, like I said, I'm going to come back to it and address it all as one piece. Okay, so let's keep on going here. So now what are we going to do? Well, we're going to take h of 6, because that is how much snow has fallen at time 6, right? And, or how much snow has, been removed at time 6. Let me move this down a little bit. And what I'm going to add to it is the snow that we're going from time 6 to time 7 of g of s ds, which equals, well, it equals this amount that was removed, that's h of 6, which is 0, plus the definite integral, well, the integral 0 to t, 0 to t of our function. What was our function? It was 125 dt. So this is going to be equal to, whoops, excuse me, I just saw that, fixing it right now. So this is going to be equal to h of 6, which is 0, plus 125, and that's going to be actually 125 t minus 125 times 6. Okay? Before we continue, let me just, I'm going to do two things. I'm going to start taking care of my inequalities because they're not quite right. And then I'm also going to, let's just talk about the second one really quickly. So let's just talk about, I'm going to highlight and then unhighlight this whole piece right here really quickly to make sure that's understood. Because if you understand that line, all the other lines should probably make sense. Okay, so in order to look at how much snow she has removed for this second part, right, what we had to do is we had to say, okay, first we need that initial quantity. How much has she removed initially, right? We need to know that. I'm going to highlight it here. So that's h of 6. That represents how much snow she's removed from time 0 to time 6. Then we have to add to that the displacement from time 6 to 7. And that's what this represents, just kind of like it did over here, except, yes, I see it. That should be a t, not a 7, because again, it's a displacement. It could be any time during that period. So that is a mistake. So one more time, since I did have a slight mistake there, let's make sure we're good. So we start with the amount of snow that's fallen at time h of 6, right? Because now we have finished this block of time. This block of time is finished, and we are now on to the next one. Oh, that's straightened out. Now, what we're going to do, what is going on there? Let me start erasing a couple things here. Okay. Now what we're going to do, so we took that block of the amount of snow that she removed, h of 6, which was 0, and we added to it the displacement from any time from 6 to 7, right? But in this case, we're saying 6 to t because t can be any time from 6 to 7. And this is what we got. Okay, before we move on, like I said, I want to deal with the inequalities. And the inequalities, they're a little different than this, okay? And the reason is we have to consider what we're plugging into our function. So for the first one, right? For the first one, we are using this integral goes from, I don't really know if it's going to matter too much, but yeah, I mean, like I said, I don't know how picky they're going to be. They're probably not going to be very picky, but here's my thought. I'll give you my thought process on whether I'm using a less than or equal to or a greater than or equal to. I bet if we stuck to what they gave us, it would probably be fine. But here, I'll give you my thought process on it. Okay, so for the first one, right, I'm going to actually go from time, I'm going to do it this way, time 0 to 6, right? Because h of 0 is captured with this, and then we are going from 0 to t, which t can be equal to, include 6 in the thing. I think you'd agree. We can take this thing and evaluate it at 6. Next, for this one, I'm going to do this, and here's why. The 6 has already been taken care of above. Okay, we already know at time 6, so we can't have them both. So we already know, when I want to evaluate how much snow has fallen at time 6, I'm going to use the first one. The second one, I'm no longer going to use that anymore, right? So that's why I'm saying greater than 6. And I'm just going to kind of stick to that theme that it ends at 7. For my next one, then, and again, like I said, is this important? I can't imagine that it is. I just want to be consistent in my problem. So if you're like, I don't understand that, I wouldn't even worry about it too much. I don't see, I mean, it's almost kind of arbitrary. I don't know if there's really a rule on it, but what I'm going to do for the next one, I'm going to go from 7 to 9, okay, including 9. Again, what the big thing that I have to do here is I can't say these two things have to be different, right? These two things have to be different because one of them has to include the number, the other one doesn't. I feel like mine is better, more exact, but like I said, I feel like that's so nitpicky that nobody's going to take off for that. So if you're like, I don't understand it, don't worry about it. Not a big deal. Okay, let's go from time 7 to 9. So now what are we going to do? Well, we're going to take h of 7 and we're going to add to it, yes, the displacement from 7 to t of g of s ds, okay? Which is going to be h of 7, am I going to have the room? I don't think I'm going to have the room. So let's do this. Let's move stuff around here. So this is going to be equal to h of 7, which is this function right here, evaluate at 7, which I think you'd agree is just, so well, actually, we could do it. We could go through and do it. So this is going to be 1, I'm going to take that function, so it's going to be equal to 0 plus 6 to 7 of 125 dt, right? But then what am I going to do to that? I'm then going to add to that the displacement, wait, this is kind of messy, from 7 to t of g of s. which is actually, let's put in the number. G of S, what is it? I think it's 108. 108 D of S, right? So this right here, just to be really clear, this right here represents the amount of snow at time 7. This right here represents how much more snow that she's, in this case, being removed. Right? Or the volume of snow being removed. I think that's correct. Sorry, I'm going to review my notes really quickly just to make sure I'm getting that down correctly, which I think I am. Okay, let's keep on going. So this becomes 125 times 7 minus 125 times 6, which is 125. Then I'm going to add to that. This is going to become 108 t minus 108 times 7. Okay, so I have 3 functions, and I'm going to kind of highlight them here. So function number 1. Let's highlight in light green. Function number 1. That represents the amount of snow being removed at time from 0 to 6. Then function number 2. Function number 2 is going to be this right here, right? I can simplify it, but it's going to be represented by that right there. And then function number 3 is that. So now let's put it as an actual piecewise function. So I'm going to say h of t equals, so let's just kind of stick with our things here. So it's going to be equal to 0 from time 0 to time 6. And then it's going to be equal to this second one right here. I'm going to simplify that just a little bit. So that's going to be equal to 125. It doesn't matter. I could keep it the way it is, but I just think it's a little bit easier to read. And that's going to be from time 6 to time 7. And then it's going to be this last one, which is going to be 125 plus, again, I'm going to simplify this a little bit. And that's going to be from time, what is that? From time 7 to, time 9. Okay? So this was kind of a rough one. I think there's just kind of a lot going on. But here's what I would say if you're having difficulty with it. For each time interval, right, in order to figure out, to come up with the volume equation, right, we have to start with, where do we start with? At time 0, we started with 0 amount of snow, right? And then we added this displacement. But at time 6, right, let me rephrase that one more time. I know I'm doing a lot of rephrasing today, but I want to make sure that I'm being exact here. So we're looking for the amount of snow that she is removing, right? So at time 0, she's removed 0 amount of snow. I think you'd agree. And that goes all the way from time 6. Now, when we look at from time 6 to time 7, we got to take the rate of change. We've got to take how much snow she's removed from 0 to 6, which is 0. And we've got to add to it the amount of snow she's removing, the displacement of snow, or the amount of snow she's removing from time 6 to, whatever we're looking for in that interval from 6 to 7. And we're going to continue that thing. So you always start with some amount and we add the displacement for each function. Hopefully that makes sense. Okay, I know it's kind of a little bit of garbly-gook right there, but I think just think of that as your most basic concept. How much do we start with? How much is being removed? How much do we start with? How much is being removed? How much do we start with? How much is being removed? There. Okay. Whoo, let's move on. Okay, let's look at letter D. How many cubic feet of snow are on the driveway at 9 a.m.? So now we're asking how many cubic feet are on the snow on the driveway at 9 a.m. So we have to take the amount of snow that's gone on minus the amount of snow that she is removing. So what I'm going to do for part D is let's start with at time 0, right? I think you'd agree at time 0, there is 0 snow on the driveway. And then what I'm going to do is I'm going to take the displacement of snow from time 0 to 9, right? So, and this is the amount of snow that's falling on the driveway. So far, I've got the snow falling on the driveway. But now, what do I have to do? I have to remove the amount of snow, remove the snow that is she's removing at time 9. Now, I think you'd agree, we've already come up with a function. This whole function right here represents the amount of snow she's removing. So I'm just going to take this thing and evaluate it at 9. Be careful. This represents the volume of snow being removed, right? Where this was right here a rate of change, which is why we had to integrate it. Okay, so from there, it's really just kind of plug some stuff into our calculators, right? This is a calculator value. This is something we can evaluate. What I came up with was 367 for f of t, I came up with 367.3346064. And h of 9, right? All I do is I just take this, I'm going to evaluate this function right here at 9. And I'm going to subtract 341. So my total answer is either 26.334 cubic feet or 26.335 cubic feet. Okay? Okay, I know that went on a bit long, but that is problem number 24.